Welcome back, friends. This is the fifth video of the Environmental Mass Spectrometry series. In this video, we will learn about the precautions and molecular formula determination. This video series will end at this fifth video. Another advanced series might come. Anyway, let's get started with the final video. In the first video, we focused on the most abundant ion in a mass spectrum. But, is that adequate selection for any situations? Unfortunately, the answer is not. If we mistake it for an improper ion, we will fail in its molecular formula determination. So finding the proper ion of interest is important. In order to determine molecular formulae, we focused on the most abundant ion first, then, the adjacent isotope ions. In the mass spec, the exact mass of the most abundant isotope of an element is termed monoisotopic mass. Similarly, the monoisotopic mass of a molecule is the sum of the monoisotopic masses of the elements in its chemical formula. As for most common elements, the monoisotopic mass is the mass of the smallest m/z isotopologues. But, some elements like lithium, titanium, and chromium, the smallest m/z isotope is not the most abundant. Fluorine, sodium, phosphorus, and some other elements have no stable isotopes. They are termed monoisotopic elements. Among 83 naturally occurring stable elements, 20 elements are the monoisotopic elements. Beware that, you should not mix up an analyte's monoisotopic ion with the unintentionally produced fragment ion. An atmospheric pressure ion, API source like ESI, is definitely a soft ionization technique. Most ions obtained by the API can keep them intact, and only a few ions cannot keep it intact, resulting in its fragmentation. Please see the extracted ion chromatograms, shown on the upper left side. These chromatograms were obtained simultaneously. A standard solution of a pesticide dinoteffuran was injected into a LCMS. The standard solution contained dinoteffuran only. Nevertheless, an unknown ion of m/z 157.1210 was observed as well as dinoteffuran. Their retention times and peak shapes were identical. This is because dinoteffuran eluted from the LC column was dissociated itself in the mass spectrometer. A possible reaction pathway is illustrated on the bottom of this slide. The nitro group of dinoteffuran must be dissociated in the mass spec. This unintentional dissociation can be attributed to a phenomena, in-source collision-induced dissociation. In-source collision-induced dissociation is a dissociation of an ion, as a result of collisional excitation, during ion transfer from an API source to the vacuum chamber of the mass spec. The observed fragment ion is inherently not an analyte's monoisotopic ion, so we must confirm the focused ion is intact. Our three-step manner to confirm intact ion is shown here. For careful determination of molecular formula, you should check the multiple adduct forms of the focused ion, the ring and double bond equivalence, RDBE, and the nitrogen rule. The formation of multiple adduct forms indicates that the ion you focused on is not fragment ion. If it is a fragment ion, its dissociation reaction may depend on its adduct form. The different adduct form may cause the different dissociation reaction, and the different dissociation reaction may produce the different fragment ion, giving the different m/z. Particularly in the oppositely charged adduct form, the dissociation reaction may be different. In the next step, we will check the ring and double bond equivalence, RDBE, which can be calculated according to the equation on the upper right side, where X is the number of valence 4 atom like carbon, Y is the number of valence 1 atom like hydrogen and halogen, Z is the number of valence 3 atom like nitrogen and phosphorus. Let's see the RDEB of dinoteffuran analogues. The RDBE of the protonated form is 2.5, the deprotonated form is 3.5, the protonated fragment ion is 2. The ionized intact molecular ion by API, I mean the protonated and deprotonated intact dinoteffurans, give the RDBE ending with 0.5. On the contrary, the protonated fragment ion gives an integer RDBE. This is because of an open shell ion, produced by a homolytic bond dissociation of the nitroguanidine moiety of dinoteffuran. If you find an integer RDBE valued ion, in spite of ionizing by an API source, it must be an unintentionally fragmented ion. So you must explore its intact molecular related ion. Please be notified that closed shell fragment ion also has the RDBE ending with 0.5. The RDBE ending with 0.5 is not the evidence of an intact molecular related ion. The final step is checking the nitrogen rule. Except for nitrogen, the common elements having an odd number of valences also have an odd mass numbers, such as hydrogen, carbon, oxygen, etc. Similarly, the common elements having an even number of valences also have an even mass numbers, except for nitrogen. Nitrogen represents this only exception. This is the nitrogen rule. Let's have a look at the table. Hydrogen has an odd mass number, and an odd valence. Boron also has an odd mass number, and an odd valence. Carbon has an even mass number, and an even valence. But, nitrogen has an even mass number, and an odd valence. The other elements also obey the nitrogen rule. The ionization technique will dictate how the nitrogen rule is applied, because whether a closed shell ion is produced, or an open shell ion is produced, depends on the ionization technique. For instance, electron ionization, EI, produces an open shell ion. Open shell ion has an odd number of electrons. As for open shell ions, in the case where a compound contains an even number of nitrogen atoms including 0, its m over z value must be an even number. On the contrary, in the case where a compound contains an odd number of nitrogen atoms, its m over z value must be an odd number. Let's look at the table on the slide. The compound containing an even number of nitrogen atoms possesses an even m over z values. The compound containing an odd number of nitrogen atoms possesses an odd m over z values. On the contrary, electrospray ionization, ESI, produces an closed shell ion. Closed shell ion has an even number of electrons. As for closed shell ions, in the case where a compound contains an even number of nitrogen atoms including 0, its m over z value must be an odd number. In the case where a compound contains an odd number of nitrogen atoms, its m over z value must be an even number. Let's see the table. The compound containing an even number of nitrogen atoms possesses an odd m over z values. The compound containing an odd number of nitrogen atoms possesses an even m over z values. That's all. Thank you for watching.